Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Sinyu Tan, Norah Tan, to give us a talk on the incompressibility and spectral gaps of random circuits. So Norah is a math PhD student at MIT, and she is co-advised by Aram Harrow and Peter Shore. She got her bachelor's degree from Duke University. This is like 2 years ago, and she has broad interest in quantum information topics with a recent focus on unitary designs. So Norah, the floor is yours.
Thanks for the introduction. So thanks all for coming. And today I'm going to talk about this recent work on incompressibility and spectrum gaps of random circuits. This is joint work with Anthony, John, Jonas, Yunchao, and Tony. Okay, so I'll start with an outline. So this talk will have 3 parts, with the first 2 parts being explaining the 2 terms in the title, incompressibility and spectrum gaps. And in the incompressibility section, I would mention no technical details and try to make it as intuitive and natural as possible. And we'll first start with what does it mean by incompressible or compressible, and what the statement random circuits are incompressible means. And we'll also talk about what is a design and what does this linear in T scaling means. And then we'll talk about this random quantum circuits form T designs, like the construction with linear in T number of gates. And this construction essentially is based on the spectrum gap argument. We'll also talk about what is this spectrum gap definition, etc. And in this talk, I'll focus mainly on random quantum circuits, like unitary circuits. But our paper and our result essentially also solve the question of classical reversible circuits in the setting of classical reversible circuits. And it corresponds to the concept of T-wise independent permutations. And the starting point of both the incompressibility of random unitary circuit and classical reversible circuits are both based on this Kassabov expander. So it's like a backbone of both. And essentially the classical result is a easy adaptation of this efficient implementation of the expander on the alternating group. So let's get into the first part. What does it mean when I say a circuit is incompressible? So we start with the very fundamental definition, a natural definition of the circuit complexity, which is the minimum number of elementary gates to implement this operator U approximately in operator norm. And it's like this, the error described by this delta. And very generally, this U can be an n-qubit unitary. It can also be a Boolean function. Or it can be what I was just saying, like a reversible classical circuit that is a permutation 2 to the n times 2 to the n permutation. So it's really giant. It's not like only permuting the bit. So you would imagine it to be pretty complicated. So suppose I tell you that this U can be constructed explicitly with these gates, these L gates. So in other words, I give you a circuit description of this operator. Can you tell me if U can be compressed? And in other words, does there exist another decomposition of U that is using fewer than L gates? And if you can give me if there exists such a decomposition, then it can be compressed. But if you cannot be compressed, if you can show it, you can prove it, then this tells you that the circuit complexity of U equals to L, because you start with that explicit form decomposition of U. So the question of circuit's lower bound, like proving circuit's lower bound for some specific function is an extremely hard problem. Intuitively, this is like saying you need to show that any smaller than L circuits cannot be used to construct this specific circuit, this specific function. So that's extremely hard. And maybe an easier question to ask is, okay, suppose my circuit or function is completely random. What is its circuit complexity? And the answer turns out to be very easy. So this is a screenshot from the Wikipedia page of circuit complexity. And it says that this question goes back to Shannon in 1949, who proved that almost all Boolean functions on n variables requires an exponential circuit size. And in other words, this is saying a random function is complex. And similarly, you can have a completely analogous claim for unitary circuit, saying that a hard random unitary is also complex. And more specifically, you can also say that, almost all the states, both the states and unitaries have exponential quantum circuit complexity. And this is, I think, Nielsen and Tron has a proof of this fact. So now we are given two problems related to circuit compression. One is proving lower bounds for a specific function. This is known to be extremely hard. And then is proving circuit complexity for a uniformly random function. And this is easy. So we would want to find something in the middle. And
sorry, can I just interrupt
yes.
for a while? I just wanted
Yes.
to have like, I mean, I do agree with this kind of result. I am familiar with it. Do you have like a sort of, since I'm a physicist by training, do you have sort of an intuition why it would be like why this has this kind of complexity for the hard random unitary, for example?
So this is essentially like a counting argument. So if we take the example of like a random Boolean function, there are exponentially many of them. And this just means that if you count the number of functions or circuits with like a polynomial size, you cannot reach, so by sampling only from like a low depth, you cannot saturate. This is like a very, very small set compared to the entire space, because the entire space is like exponential. Yeah. So in other words, if you just sample randomly with high probability, it has to be very complicated.
Okay. I see.
Yes.
Okay. Thank you.
Good question. Okay. So an intermediate question in between is, suppose our U is generated by L random gates. Can you compress it? So it's a combination of the randomness and some sort of fixed function, some sort of specific function. And in today's talk, we will be dealing with this random circuit model all the time. And we assume the most general form of it, where each step you apply a hard random 2-qubit gate. And we assume the qubit connectivity can be arbitrary. For example, it can be in breakwork, or it can be in O2L connection. And in our paper, we actually prove this incompressibility result regardless of what any like geometry. So now we're able to state our first theorem, which is the linear growth of robust quantum circuit complexity. The result is, with high probability, a random quantum circuits on n qubits with L gates, where L can be exponentially big, this circuit cannot be implemented approximately by any quantum circuit with fewer than L over poly n number of gates. So So this result is, so one thing, there are several things about this result. First, note that this L goes up to exponentially big. So this is why this compression makes sense when we say that it is not compressible, even though there's a poly n factor in L. And the second thing is this approximately. So this is essentially a strong notion of incompressibility, because if you require if you delete this approximately and substitute it with exactly, then this has already been proved by Jonas Hafferkamp and other authors a few years ago, and they can all show it for the robust quantum circuit complexity case. In other words, random quantum circuits are incompressible. Are there any questions so far? Should I continue?
I think. Oh wait.
Oh yeah. Can I ask a question? Like when you mentioned
Yes.
about random circuits, can I also consider it as a hard random unitary, or is it a bit different?
So this circuit model is each step you are like a 2-qubit hard random. So it's not like is like a local random. You want it to be as easy and simple as elementary as possible.
So each local unitary is a hard random unitary.
Yeah, it's like a hard random SU4. It's a 4x4 matrix, and then with like tensor a lot of identities.
I see. Okay. Thank you.
Okay. So this is what it means by random quantum circuits are incompressible. And now, what is a T-design? So a unitary T-design, it refers to a probability distributions on the entire unitary group. And you want it to be statistically indistinguishable from the Haar measure. So if we assume, if we think of the entire unitary group as a high dimensional sphere, where each point corresponds to a unitary, then the Haar measure is a uniform measure on this high dimensional ball. And your design, it's something you're trying to get close to being uniform as possible. And it could be continuous, it could be discrete, but you also want it to be efficient, because Haar measure itself is complicated. And more concretely, how do you measure this statistical closeness is through moments. And you want the T's moment of this distribution to match approximately with the T's moment of the Haar measure up to this epsilon parameter. And a very common model to generate a T-design is through random circuits. So intuitively, if we start with a generating set, in our random circuit model, the generating set is each time you pick you pick 2 qubits at random and then you apply SU4. This is a very natural generating set. And if you like apply many times, you would imagine that eventually it will mix everything uniformly. So it will approach the Haar measure. And the random circuit model is exactly building on this. So suppose we have L IID gates, where each gate U sub I is drawn from this distribution nu. And in this brickwork model, so mu, you can see that is correspond to these 2 layers, and we sample 3 steps. And if we sample it for L many steps, and we send L goes to infinity, then this eventually will become the Haar measure. So a common recipe is first, you want to start with the good generating set, meaning that it has to be universal, because otherwise you cannot, if it's not universal, you cannot approximate everything. And then you want to calculate and prove a convergence rate, saying how many L how many gates do you need to get a T design with this matching moments epsilon and T. And very naively, because yeah, let's first look at the statement first. This lemma says that with high probability, a random unitary sample from a T design has circuit complexity at least order in T. This is basically saying that if you sample from a T design, then this gate also needs to have some high probability. And naively, because a hard random unitary is complex, and we want our T design, this distribution, to be close to being hard random. This means that we would expect this T design to be also complicated. And this circuit complexity is determined by T. This lemma, we didn't prove this lemma. Well, it's like a existing reduction argument. So not, yeah, it's standard. So if we do a simple substitution, suppose we have a design, a T design, that can be constructed using order n to the a, some poly in n times T random gate. So this is like a term linear in T. And if we change this order n to the at with L, we do a simple change of variables. So if our random circuit U has L gates, then this T would be L over n to the A. So it is a L over n to the A design. And then we apply our lemma. This tells us that the circuit complexity of U is L over poly n. So this means that if we have a linear unitary T design, then we'll naturally have the incompressibility. Random circuits are incompressible. So for theorem 2, we give explicitly a construction, or like a proof is not, the construction is just two local O2O random circuits, but we prove that it forms an approximate T design with a constant multiplicative error L when L is T times n to the fourth. And this moment can goes up to exponentially high. So we can ignore this multiplicative error for now, because I'll talk about it in a few slides. There's two more things that I want to mention about this result is this linear in T times poly n number of gates also holds for any connected architecture, as I've mentioned. And it also holds for not only two local gate set, but any universal generating set. And this is also via known reduction. Yeah, so essentially this is a pretty general and strong result. Okay, so before I move on to part 2, are there any questions?
So sorry, I still am not so sure what you mean two local here. You mean all the circuits are constructed from two local circuits gates, and
yeah,
you can
sorry, go ahead.
And then you are, and in the remark you are extending them to any other gate larger than two local. That's what you mean?
Yes, so the local is with respect to your qubit connectivity. So you can assign nearest neighbor connectivity. So essentially you have like a chain. You can also have periodic boundary. You can also have a tree. So these are the underlying connectivity is defined by a graph. And in this statement, the underlying connectivity is all to all. So it's like a complete graph. And two local meaning that if your two vertices are connected, then you can apply this gate is allowed. You can apply a gate on these two vertices. So it's not it's not too is too local is with respect to a kind of your defined connectivity.
So it cannot be far connected, right? You do not allow that.
No, it's only if your two qubits are connected. But in an all-to-all connection, every two qubit is connected. So this too local just means that you can apply any SU4.
I see.
Yeah. Cool.
Cool. In the remark, are you extending to larger group other than SU4?
Yes. So generating so in this theorem statement, this generating set consists of all the two qubit gates. But I am saying that you don't need to use any two qubit gate. You can just use any universal gate set. For example, like a Clifford plus a single non-Clifford, like Clifford plus T, say. And this would also hold in that scenario.
I see. Okay, cool. Thank you.
Okay. So now for the second part of spectrum gaps, this is defined with respect to a distribution. And this slide may get a little bit technical, so bear with me. Suppose we have this distribution nu, which is like this distribution for one step, and the gap is defined to be this operator. Let's look at it very in details. So this operator is an average over all the Haar matrices, Haar random matrices, and you evaluate it on this U tensor U bar, where bar is the complex conjugate, and then you take the T's power, tensor power, this entire thing. So U is of size 2 to the n times 2 to the n, and you have 2 copies, and then you have T copies, so you have 2 T copies. And this matrix is really big. It's like 4 to the n times T. And you have such a big matrix, and it is Hermitian. But this matrix is just a projection, orthogonal projector. So it has eigenvalues only 1 and 0. And we actually know exactly what this operator looks like what are the eigenvalue 1s corresponding to. And if you know a little bit of representation theory, you would see that this U tensor U bar tensor T thing is a representation, and is a reducible representation, meaning that it can be broken down into ERAPs, and essentially these two terms can be simultaneously blocked, diagonalized according to your decomposition. And what's more, they share the same eigenvalue 1 space. So the eigenvectors that correspond to eigenvalue 1s are the same. So if you take the difference, all of them cancels out. So this thing, because all the eigenvalue 1s are canceled out, this thing will be 0. So essentially, this infinity norm, which is the largest eigenvalue, will be the second largest eigenvalue of this operator. So I say the spectrum gap will be the largest eigenvalue of this thing, which is 1, is 1 here, minus the second largest eigenvalue of this thing. So the second largest eigenvalue is the essential norm. And it's very reasonable for us to call it the spectrum gap. So it's like λ1 minus λ2. And if you have a spectrum gap, then you will see that if you have a convolution of nu for L times, you apply the gate for L times, this one gives you like an exponential suppression. And essentially, this is telling you if you have this delta being your spectrum gap for nu, and then with 1 over this gap times linear in n and t time, So 1 over inverse and gap times n times t will give you like a t design. So if we want to show a linear in t design, it suffices to give a t-independent spectrum gap, because your linear factor is already coming from this additional dimension suppression factor. So this will be our goal. We want to show that two-local all-to-all random circuit, one step has a spectrum gap that is inverse polynomial in n, and that it is independent from t. Okay. So before we move on to two-local, dive into two-local, we actually will start with a more structured ensemble. So it's called PFC ensemble. And this work is like proposed in this paper, simple construction of linear depth T designs and pseudorandom unitaries. And it has been the starting point of many other works. For example, this incompressibility result, as well as the pseudorandom unitaries result by Fermi-Man and Robert Huan. What they show is that this PFC ensemble forms an additive error T design for an exponentially large T. So based on this literal difference between additive and multiplicative error, you can just tell that the requirement of having a multiplicative error T design is like much stronger. And we will really need a multiplicative error design in order to argue about incompressibility. And in the literature, most of the construction that give a multiplicative error T design go through the spectrum gap argument. And on the previous slide, you can see that it is a pretty clean argument. So this will be our essential goal. But let's first look at how this PFC ensemble is defined. It just corresponds to a C operator. You first apply a C operator, and then you apply an F operator, and then you apply a P operator. And the C is just a random Clifford. And then F is a so-called a random phase gate. So essentially, it is just a diagonal gate where you have +1 or -1 on the diagonal. So it corresponds to a Boolean function, a completely random Boolean function. And P corresponds to a random permutation. So it's just a 2 to the n times 2 to the n really big permutation matrix. And at the very beginning, we said that a random Boolean function has exponential circuit complexity. It is essentially the same with a random permutation that also has exponential complexity. So now if we want to directly use this result, there will be two problems. First, it is only an additive error design. It is which is not enough. And the second, this PFC ensemble seems very structured and nothing like a two-local random circuit. So we will need to convert it to this two-local model. So let's modify PFC. So recall, as I said, our goal is to prove T-independent spectrum gaps for two-local random quantum circuits. Our strategy has 4 steps. The first is we want to show some kind of initial, very rough spectrum gap for this PFC thing. And then, because PFC, each component is very deep and big, we want to break it down into some baby steps of local gates. This is not like the two-local hard random, but it is essentially still local. And the third step is we want to analyze the spectrum gap of one baby step. And then we will we will relate the spectrum gap of these baby steps of local gates to the desired two local random quantum circuits. So for the first step, with some norm conversion, we can show that a different ensemble, a slightly modified ensemble, has a gap t over 2 to the n over 2. So when t is like small, this gap is small. And this ensemble is CPFPC, where the two Cliffords are independently sampled and two permutations are also independently sampled. And the reason why we are adding like two more CNP is because we want the entire distribution to be self-adjoint. And this is kind of, we kind of need this in converting the gap. So converting from this additive error to a initial spectrum gap. So as for second step, we want to break it into baby steps of local gates. For Clifford, it turns out that the only thing needed in that MPSY paper is that it forms an exact two design. So for the Clifford, we can just replace it with any approximate two design with a constant multiplicative error. And for the P, this is what we will use this Kassabov expander on the alternating group result. So you can think of it as breaking down a deep uniformly random permutation matrix with smaller gates that are also local. And essentially we were using like Toffee gates. And it's kind of annoying with this diagonal face gates group because they're all diagonals, so they're like commuting with each other. And what we want is an argument that is rapidly mixing. And intuitively, what does rapidly mixing mean? So we start from one point, like one element, say identity, and then we do a random walk using our generating set. And then we go to a different point with some probability, and then we do another walk. Rapidly mixing just means that we can explore the entire space relatively fast. And this means that you cannot go back very easily. Because if you can go back, you're just redoing it and you're not exploring the new things. And if you're an abelian group, you can just go back very easily because your operators can commute. So you can, with much higher probability, you can generate like an inverse at a future step, and that inverse will cancel with something you applied in the past, and it can bring you back very easily. And on the other hand, if you have a very non-commutative group, it's very hard for you to go back, and it's easy to mix very fast. So we have a problem with this phase gate. And how do we solve it is we will just simply get rid of it completely. And how to do it is we observe that we can simulate this phase gate, random phase gate, where each entry is +1 and -1 by another distribution. So this Z1 is a fixed single poly Z. So suppose it's like a poly Z on the first qubit. Then the Z1 will be a 2 to the n times 2 to the n matrix, diagonal matrix, with the first half being all ones and the second half being -1. And if you apply a random permutations on the right and left of it, it's permuting on the diagonals. So essentially it is a trace zero diagonal matrix that with randomly assigned ones and -1. And you cannot tell, these two distributions are statistically indistinguishable up to exponentially high moments. And this means that we can just safely substitute this F with PZ P inverse. And now if we work with this distributions, we can get rid of F completely, and this ensemble is CPZPC. Or these two Cliffords are still independent from each other. And these two P's are also independent permutation, and Z is just a fixed poly. And we want to analyze the spectrum gap of this baby step. And it is defined as, so as I said, this Clifford can be substituted with any unitary 2 designs with a constant multiplicative error. So the easiest solution is just to substitute it with brickwork, and we can directly relate it to our final goal. This result is like at the very, very beginning of the study of unitary circuits using random circuits model that says linear n layers of brickwork suffice to give you like a gap 0. It's a constant gap design, 2 design, constant gap 2 design. So the ending C will also have this distribution. And for the permutations, it turns out that you can think of this baby step as sampling n cube random 3 cubic gates. That is due to Kassabov. And this roughly is because we used some modification of Kassabov. Like we built on Kassabov's construction and do some manipulation to adapt it to our setting. And there are 2 independent permutations, so you just do it twice. And then Z is just one fixed single poly. And we can show that the spectrum gap of a baby step is a constant. So now our random circuits look less structured because we have already decomposed each component into some very, very local gates. And this baby step essentially has n to the 3, like n cube number of local gates in total. But each individual gate is still, even though it's local, it's still not hard random. And this is essentially the job of step 4, which is to relate this gap to the gap of 2 local random circuits. We essentially generalized the tool that is developed in this paper using that is based on detectability lemma and quantum union bound. And this lemma says that suppose we have m subgroups and each only act on constantly many qubits. So they are in some sense also local, and it's constant local. And then if this thing has a gap lower bounded by delta, and uniform means that it is sampled from this group with element uniformly at random, this distributions, and then you first sample from G1, and then you apply a gate from G2, and then you apply a gate from GM. So this very fixed distribution has a gap lower bounded by delta. If that is the case, then using this a synthesis of detectability lemma and quantum union bound, we can show that the 2 local all-to-all connection model is lower bounded by delta over m, and m is the number of gates you have. So if we plug this lemma back to our previous slide, like the spectrum gap of baby steps, then essentially we will have n to the cube subgroups. So if we go back, so each fixed position, fixed gate correspond to like a subgroup, and you all have n to the cube many of them. And this spectrum gap is constant, so delta is constant. So it will tells us that the spectrum gap of 2 local random quantum circuit is 1 over n to the cube. And this completes our purpose of proving a inverse poly n t-independent spectrum gap. So this is the last slide of part 2. Any questions so far? Okay, so part 3, this Kassabov expander. I want to first explain what do I mean when I say an expander on the alternating group. So the alternating group is a subgroup of the symmetric group where you only consider even permutations. And the alternating group and the symmetric group are like they match on exponentially high moments. So without exponentially many copies, you cannot distinguish them, in other words. So we'll be working with alternating groups. So the expander usually the context is of infinite families of pairs, with the pair matching the group and a generating set for the group, Sn. And the family of the associated Cayley graphs is expanding. So what is a Cayley graph? It is defined, the vertices are the elements, and the edge, meaning that you can get from this element to the other element through one something in the generating set. So this is an example from the Wikipedia. The Cayley graph of the dihedral group generated by a order 4 rotation and a order 2 reflection. So if you have a Cayley graph, then you naturally have adjacency matrices, and if your Cayley graph is expanding, in other words, your spectrum gaps of the associated adjacency matrix are nicely bounded. And if we write it out in our tensor product kind of language, it means this P tensor T thing is lower bounded by inverse Sn. This is what it means by expanding. And these 2 papers by Martin Kassabov, they initially came out in 2005, and they were published after 2 years of review. Inventia Mathematica, very like some very well-known math journals of high standard. And the result is one of the results that he gives is an explicit generating set of constant size that is rapidly mixing, so like an expander, for each n. So compared to the previous slide, because this generating set is constant, so Sn is constant. And if you plug this in, it means that this gap is also a constant. So spectrum gaps are constant. But the question is, can these generating sets be efficiently implemented? Because essentially, we only care about n being like a power of 2, like 2 to the small n. And we want our so we only care about the capital N being a power of 2, and we want each generator in this set to be implemented with poly small n. So it's like polylog big N, number of simple gates. This is not answered in Kassabov's paper. And we give a theorem that says these generators with modulos and modifications that are short reversible circuit. For any small n, each generator in this S2 to the n can be implemented using order n linear n number of NOT gates, controlled NOT, and Toffoli gates without any epsilon. So this theorem is, like I said, the building block of our quantum random circuit result. because we are substituting the permutations with Kassabov expander. Okay, so as a summary, we proved that random quantum circuits form multiplicative error unitary T designs with linear in T number of gates, and the dependency on n is poly in n. How we showed it is we convert this PFC ensembles break it down into baby steps of local gates. And we proved a independent spectrum gap, a T-independent spectrum gap of a baby step, where this P is based on an efficient implementation of Kassabov expander on the alternating group. And with this linear in T unitary design, we show immediately that random circuits are incompressible, aka the linear growth of robust quantum circuit complexity. So that's all of my talk today. Any questions? This is the last slide.
All right. Okay. Thank you very much for very interesting talk, if a bit technical. Yeah. Yeah. So now okay, we have quite some time for questions. So if you have any questions, you can just free to basically unmute yourself. Ask them now. Okay, maybe I can start with one question for myself. So yeah, because like in the previous slide, you mentioned something about this efficient implementation without requiring an ancillary, right? So it just reminded me, like, so in the incompressibility result, so this is also like, even if you allow ancillary bits, it cannot be compressed. Because, okay, I don't know, like, I'm just imagining that maybe in some cases, by allowing ancillary bits, you can use fewer gates, but I don't know if that's actually that actually happens.
Okay. So first of all, the discussions, I've never thought about including ancillary bits, but I think the discussion will definitely be more complicated because you can have many levels of assumption. Say, I allow constantly many ancillary bits, or I allow linearly poly, or like any ancillary bits.
But I suppose anyway,
Yeah.
like because you're only also requiring like certain small gates, and then maybe it's at least like my intuition is it won't help you so much. Yeah, but you're right. I mean, I guess that there's sort of like it gets a lot more complicated since you can ask more.
Right. I've never thought about it, so I don't want to give like an answer that
sure
may not be right. But this question of whether random circuits can be compressed or not, or like the linear growth, this rate was initially conjectured by Brown and Susskind in 2016 or some a while ago, and it was we proved the exact setting without like and their conjecture didn't have any ancillary bit in the description, I think.
Okay, I should let other people ask first.
Yeah, thank you for your nice work and presentation. Probably I kind of get lost in the T-independent spectral gap in the baby step. So why you are kind of get rid of the T-dependence of the proof? Why there are T spectral gap?
So why? So I don't know if you agree with me that the bottleneck of breaking this down is actually in the P, because if we have another way of having an expander or like a T-independent spectrum gap in the permutation setting, then this would also imply that random two local circuits have a T-independent spectrum gap. but people, this was an open question in the theoretical computer science community. People are aware of Kassabov's paper, but nobody has really looked into it and thought about whether it could be made efficient. And it turns out that it could be made efficient. So that solved the problem in the TCS community. And then we figured that if you have a spectrum gap, T-independent spectrum gap in the permutation group, or like symmetric group or alternating group, then you can use that result to make the unitary group's gap also T-independent. Is that what you're asking? Does it answer your question?
Yeah, kind of, but I need to think it more. Yeah.
Right. So our paper is like quite long, quite dense, and I was trying to give like a high level intuition of why this thing works. But in the end, there's like a lot of nitty gritty like change, conversion of norms that is going on underneath.
I see. So you basically say that the open question is solved, that T independence is kind of important and been proved.
Right. So the linear in T result is essentially tight. So there's a lower bound and there's the upper bound, and then now they're like linear, they match. So the linear bound is the lower bound is essentially given by this. If this is lemma at the very beginning, if you have a T design, then every gate has circuit complexity T. This is the lower bound, and now we give a T design that is linear in T, so the T dependency is resolved.
I see. Okay, good. Thank you.
Yeah, thank you for the question.
I want to ask another question. I'm still not understanding quite well how you, the estimate of spectral gaps has to play a role here. Like,
so this is also a common technique in Markov chain mixing, if you're familiar. So if you have a Markov chain, Markov process, and you want to know how fast it mixes or it goes to a stationary distribution, you analyze the spectrum gap of your Laplacian. And then the spectrum gap will tell you how fast. It gives you some kind of guarantee. It's like a clean statement to how fast it mixes. You can also evaluate it from some other perspective. For example, the definition of an additive error design is based on diamond norm. And the diamond norm is very intuitive. It has operational meaning that compare the two quantum channels from an operational perspective. You can also look at this definition of the diamond norm and calculate it from your distribution without using the spectrum gap. But that would most of the time be way more complicated than a spectrum gap argument. Plus, it cannot give you multiplicative error. So the spectrum gap is essentially the only tool that you can use to navigate through a multiplicative error design. There's no other ways that I know of. Or is that what you're trying to ask? Or you're interested in why?
So here you're using the spectral gap to like try to gauge how fast it mixes.
Yes.
Okay.
So this L is very clean, as you can see. So you just like order. There's like no hidden factor. It's just 1 over this gap times nt plus log 1 over epsilon. And there's no other conditions on how big your t needs to be, how how your n should look like. It's just a very straightforward argument based on spectrum gap. This quantity.
Maybe another naive question. So does this spectral gap has to do with the order of, because in your summary you said that you proved that random quantum circuits, they form a multiplicative-error unitary T design with that much of gates. So is this number of gates has to do with the spectral gap that you just give an estimate? Not really.
Last slide. Sorry. Oh.
I,
Okay. Which part you're talking about? This poly n?
yeah, the poly n. Does it has to do with this?
So we have so the theorem states it in terms of n to the fourth, and we have other arguments that reduce it to n to the square, and with some polynomial factors. And this reduction is known, is in the work by Brendel, Harrell, Horodesky in 2013, that they can suppress this poly n into n square number of gates. And there is another paper that came out in the summer after our paper called Random Circuits in Extremely Low Depth, where they essentially make this poly n into log n. That is a very surprising result. And how they get that result is also used this result, because otherwise they cannot get the linear in T dependence. And they are more focusing on, their depth is log n, and each step has n number of gates. So what they have is like linear in n modulo polylog factors, number of gates.
Yeah. Okay. Yeah. Thank you so much.
Okay. That answers your question.
Yeah, it answers this. Thank you.
Right. Okay, I don't know if there's anyone else with questions. Actually, I was just curious, like, so yeah, like for this result, so the one that you actually prove is the one with n to the fourth. So it's sort of like for a particular, is it like for a particular architecture or something?
That one is with respect to all-to-all connection.
Oh, all-to-all. And then
Yes.
is it sort of like in order to get from all-to-all to sort of like the more general case, is are you trying to sort of rewrite the general case in terms of that result? Not necessarily.
Oh yeah, we reduce it. So given an arbitrary connectivity, the gap can be reduced to the all-to-all gap with some poly n factor.
Okay.
Yes.
Yeah, I imagine that some kind of this trick is
Exactly,
being used
yeah.
somewhere. Yeah. Okay.
Yes.
All right. Yeah.
Sorry, I just want to clarify. When you mention all-to-all for two local gates, it means the all-to-all is connected because you put all possibility of two local gate nearby gate, or it can be like the first and the last, not last, if not periodic. I mean, far away connection. Just
like all-to-all is like every two qubits are connected.
Oh, I see. Okay,
Yeah.
good. Thank you.